Hi, Brendan here with another training video. This one is for selecting a lead acid battery and inverter. This will be particularly useful to students doing their grid connected with batteries design task. Let's get started. So selecting a lead acid battery takes a few steps. Okay, we need to complete a load analysis and work out what our energy requirements are, what our max demand is, and what our surge demand is. We need to select a battery bank voltage, and we need to select a depth of discharge. Once we've got all those figures, we can then select an appropriate battery and inverter. So let's look at our load analysis. You can see here we've got all the customers' loads, how long they're using for, the power factor and the surge factor. Right, so the first thing we work out is the amount of energy required. So when we're saying energy, we mean the amount of storage, okay, the amount of energy that needs to be stored. So to do that, you just multiply your power, watts, by the hours of usage, and you will get the watt-hour value, the amount of energy that needs to be inside the battery. So we can see here we need 8,850 watt-hours of storage. Then to work out our maximum demand, which is in volt amps, we then do our power and we divide that by our power factor. Okay, so for example, you can see the microwave there. We've done 2,000 divided by 0.6, and we get 3333.333 recurring volt amps required for the microwave. So that's our maximum continuous output required. And then finally, we need to look at our surge power. So to calculate surge power, we multiply our maximum demand figure that we've just worked out, and we multiply that by our surge factor. And that will give us our surge power requirement in volt amps. So we can see from our load analysis we need 8,850 watt hours or 8.85 kilowatt hours of storage. Our system needs to be output 7.42 kVA continuous, and it has to be able to surge to 11.59444 kVA. So first thing we want to do is we want to select an inverter. Okay, now this isn't the same order things are done in your design task. So I recommend when you do your design task, make sure you read the whole thing before you start answering questions, so you don't have to redo sections of it. So we're going to select an inverter first. When we're looking at the inverter, our energy requirement is not relevant. Okay, we don't care. We're not worried at this point about how much energy we need to store. We just want to make sure the inverter can output the required current. And we will have a look at the Cellectronic SP Pro range for lead acid batteries. So knowing that we need 7.4 kVA continuous output, we look at the continuous line on our spec sheet, and we can see that this inverter here, the SPMC 482-AU, has the required continuous output to supply the maximum demand, and we needed 11.4 kVA approximately for our surge demand, and we can see that this inverter can output up to 18 kilowatts for 30 seconds, so it will also meet our surge requirements. So we're going to select the SPMC 482-AU as the inverter we're going to use, and you'll note that we have selected this is a 48 volt inverter. So by virtue of selecting this inverter, we've also selected our battery voltage. Okay, so our battery bank is going to be a 48 volt battery bank. The next thing we need to do is we need to work out what our depth of discharge will be. So depth of discharge is to do the further we discharge a battery regularly, we will reduce its lifespan. Okay, so we need to make sure that we don't discharge our battery too far, so it lasts a decent amount of time for a customer. So let's assume that our battery needs to last 10 years, and we assume the battery is going to cycle once per day. So we do 365 days times 10 years, and we see we need 3,650 cycles lifespan for the battery. Then we're going to look at a depth of discharge curve. Okay, so this is the depth of discharge curve for the batteries we're going to be looking at, the Sonnenschein batteries. Okay, we'll round that up to 4,000 cycles. So we want the batteries to last 4,000 cycles. They should last over 10 years. We follow that line up. And we're going to be using IUI charging. Essentially, IUI charging is smart charging. Okay, so an SP Pro is more than capable of doing smart charging. And we can see we want to be doing around a 45% depth of discharge to ensure that our batteries will last 10 years. Okay, now we've selected our inverter, we've selected our depth of discharge, and we've selected our battery voltage. We can now go ahead and actually select which battery we're going to use. So the first thing we want to do is make sure that the battery we select can store enough energy. Right, now for the energy requirement, we use the C10 rating of the battery. That's what we have to compare it to, the 10-hour rate. Now spec sheets are in amp hours, so we need to convert from watt hours to make sure we can select the battery from the spec sheet. So to get it in amp hours, we do watt hours divided by our battery voltage will equal our required amp hours. We needed 8,850 watt hours. We're doing a 48 volt battery bank, so we do 8850 divided by 48, and we can see we need 184.375 amp hours of usable energy in our batteries. But now we need to apply our depth of discharge. Okay, so we selected a 45% depth of discharge. We need 184.375 amp hours usable. So to calculate our total energy requirement, we need to do usable energy in amp hours divided by our depth of discharge, which will equal our required battery size. So we do 184.375 divided by 0.45, and we can see we need 409.72 amp hours at C10. So we go to our battery spec sheet, and all the spec sheets are in the notes below the video, so you can access all of these yourself. And we look for our battery that will be big enough, that has our 402 amps required. Sorry, not 402, it was 409 at C10, and we can see that the A602625 is going to do the job at this stage. So at this stage we think this is the battery that we're going to select, knowing it can store enough energy. But can our battery provide the continuous and the surge current? So to compare to make sure our battery can provide the maximum demand or the continuous current, we need to compare that to the C5 rate of the battery, and we need to compare our surge demand to the C1 rate of the battery. Now I am aware that our volt amp figures take into account power factor, and a battery does not provide reactive power. However, for simplicity's sake, we're just going to pretend that they do. I mean, you can guarantee that your battery is at least going to be oversized. You're not going to be undersized by calculating your battery out this way. So let's do that. Let's look at maximum demand first. Our maximum demand figure is in volt amps, so we need to convert that to amps, so we know what how much current we need to be able to pull out of our battery. So we do volt amps divided by volts will equal our amps. We needed 7,422.22 volt amps continuous current. We divide that by 48, and we can see we need an output, a continuous current output of 154.62 amps. So we need to check if our battery is capable of that. So we go back to our battery, and we're going to compare it to the C5 rate. So we grab our C5 rate, which we can see is 410 amp hours. Okay, remember that a battery spec sheet is in amp hours, not in amps. So now we need to convert that, right? If it's a C5 rate, what that's telling you is that's how many amp hours will be discharged from the battery if you discharge it over 5 hours. So you need to work out what the discharge rate is over that 5 hours. So to do that, we need to convert our amp hours to amps. So we do amp hours divided by hours will equal our discharge rate. So we had 479 amp hours discharged over 5 hours. So we do 479 divided by 5, and that equals 95.8 amps. and we can see that our battery is not capable, the one that we've initially selected is not capable of providing the continuous current to our battery system. So how do we work out which one will be good? Right. The easiest way to work that is to take what our required amp is to work out what is our required amp hours at C5. Right. So we need 154.62 amps continuous. So if we do 154.62 times 5, we're going to get 773.1 amp hours at C5. Okay, so let's go back to our spec sheet and see if we can find a battery that has at least 773.1 amp hours in the C5 rating. So we have a look down our spec sheet and we can see there's one that does 834 amp hours at C5. And at this stage we think the A602 1130 is going to be the battery that's the one we're going to go with. That's going to be able to provide all the current and also have enough storage. Finally, we want to make sure that our battery can meet the surge demand. This is compared to the C1 rate. Okay, so that's the amount of amp hours that the battery can discharge over 1 hour. And our surge demand is 11594.44 volt amps, or 11.59 kVA approximately. So we do 11594.44 divided by 48, our battery voltage, and we can see we've got a surge demand of 241.55 amps. Now to compare to a C1 rate, we would have to divide that figure by 1. I think we can all do that one in our heads. All right, 241.455 divided by 1 is going to be 241.55. Go back to our spec sheet, have a look at our selected battery, and we can see that our A602 1130 does 489 amp hours at C1, which far exceeds our surge requirement. So what have we selected? We've gone through the process now. What battery and inverter have we selected given our load analysis? We have come up with one SPMC 482-AU, the Selectronic inverter, and we are going to go with 24 of the A602 1130s. The reason we're doing 24 is because it's a 48 volt battery bank, and each of the battery cells are 2 volts, so we're going to put them into a string of 24 to get to our required voltage. That's it. That is the process for doing battery selection with a lead acid battery. I hope that is helpful to my students, and as always, if ever you need help, make sure you're reaching out via email or WhatsApp.